Okay, so let's get started. And thanks everyone for showing up on this very cold November day. And so this is the last Data and AI for Society lecture for this semester. And so before I introduce the speaker, I'll give you a little bit of a preview, an overview of what MIDAS is, the Michigan Institute for Data and AI in Society. We are a university-wide organization that supports the development of AI and data science methods and their application across all research fields for both scientific breakthroughs and also for society impact. And so, let's see. Yeah, so I'll be very brief here. We have a lot of research-related programs supporting researchers across the university. We also, these days we focus on helping people adopt AI, but also do so in a responsible and ethical way. We have a lot of training programs, training faculty, staff scientists. We have a very large postdoctoral training program, probably one of the largest in the world on AI for science. And we also train graduate students through our graduate certificate program. We also build collaboration very broadly with academia, industry, and government. So this lecture series actually is our main program focused on the community at large. So it's not just University of Michigan, but it's really everybody who wants to come from the community around the area. There's no requirement for any technical background. Our assumption is that this is a lecture series for everyone with a very wide range of background. And so the lectures tend to be non-technical. And really the point is not about technical skill building or technical knowledge, but it's really about highlighting how AI and data science are transforming society and transforming lives, and what citizens need to know, and and how we can work together to shape such technology. So I want to tell you guys, interesting. I don't think the slides are updated. I thought I updated, but this is not the updated version. I don't know what happened. But anyways, coming up in the winter of 2026 will be Tim Cernak talking about AI for bioconservation, Sophia Bruckner, who will talk about AI arts and the evolution of aesthetics. And Charan Budek will talk about AI, how to use AI to support the exchange of perspectives and to support civil discourse. So Derek Van Berkel and Jeff Mornoff will talk about AI, data science, and their work with Detroit, especially for the Detroit's challenge to the U.S. Census. We have one more generative AI tutorial left for U of M people here. Upcoming next week, next Monday and Tuesday, we have our annual Data Science and AI Summit. All are welcome, whether you're at U of M or not. We're featuring 5 really prominent speakers. I'm not going to go over each of them, but 2 of them are physicists, physics astronomy researchers. One is a healthcare researcher. One is an economist who will talk about AI and the future of work and the meaning of work. And one is a managing director of Microsoft Research. So, and we also have a leadership panel. So at the symposium on next Monday, featuring Vice President for Research and Innovation here, Vice President for Information Technology, the Dean of School of Information, and also Associate Vice President for Research. They will talk about AI at U of M, what's happening, what we can expect here locally. So I hope to see many of you next week. Okay, housekeeping items for today. Bathrooms can be found on the other side of the commons area across from this room, meaning which direction? Over there. Okay. In the event of a fire or evacuation, please exit through the doors on your left and proceed to the external doors and out of the building. After the lecture, there will be a question and answer session. Please wait for a staff member to hand you a microphone. And to accommodate as many questions as possible, please keep your questions concise. And then if your question requires extensive background or explanation, consider talking with the speaker after the question and answer session is done, okay? So today's speaker is Professor Mosharaf Chowdhury of Computer Science and Engineering at the University of Michigan. He also leads a multi-university collaboration called the ML Energy Initiative. His current research focuses on optimizing the energy consumption of AI and data privacy. He's done some really impressive work developing AI stacks that are very, very energy efficient. And also for those of you who are experienced in programming and computational work, you might want to know that he was one of the original creators of Apache Spark. So at this particular time when we're all concerned about energy consumption of AI, but also curious about how we can use AI to improve energy efficiency, Mosharaf is really one of the best people to speak on this topic.
Thank you. Give me 1 second to put this on. Okay. So I'm going to talk about our works that we've been doing for the last almost 5 years now on how to get closer and closer towards something that I call energy optimal AI. We don't really know what is optimal here, but we want to get there. So it's more aspirational than a solved problem. Unless you are living under a rock, you have seen all of these different kinds of headlines. They started toward, I think, around the end of 2022, but more so in 23. They used to be something like AI is going to take over the whole world and so on, and we need so much energy that's more than the earth can provide. And our work sort of, even before all of these things started to pop up, our work focused on trying to very precisely measure how much energy actually sort of goes in sort of training AI, doing AI inference, and so on. Many of these articles back then were based on very crude estimations, and they didn't really have any proper way of measuring. So we built one of the first systematic framework where you can very precisely measure at the level of individual queries how much energy does a query take, assuming you have access to the hardware and the query and you can run them, then you could measure them. And so we wanted to understand clearly exactly how much energy are we talking about. And so over the years, what has happened is that the conversation changed a little bit over 24 and now 25. You see more and more these kinds of articles showing up that we did the math and we know exactly how much energy is being consumed and so on, because some of the tools are being built by us and other groups throughout the world. And actually, this MIT Tech Review article, we worked with them for almost 6 months to measure for some of the popular open source model to exactly know like how much energy is being consumed for inference. And of course, energy is on all of our minds because you have seen the other news that are around us where all of these big data centers are being built and they are going to need power and energy that can support hundreds and thousands of homes and so on. So the talk today, I'm going to focus on how much energy does AI actually consume for the cases when we can actually measure and know. And then why does AI consume so much energy? And what can we do to reduce the energy consumption and all the work, some of the work we have done. But before going there, for those who are not very familiar, I just want to boil down the entire world of AI. They will all be mad at me to simply this one slide. Essentially, what AI is trying to do is getting vast oceans of data and collecting from all possible sources. And then we are training something called a model on hardware devices. Oftentimes it's GPU that are produced by NVIDIA and AMD. I'm sure people by now are familiar with the name NVIDIA, at least given they are always on the news. But essentially that's what AI is. You take a lot of data, you have a model, you run them through a lot of computation devices, and then you end up with a trained model. Once you have the trained model, you can use the trained model to send a query, and the model produces a response that if you have used any of the commonly available AIs, like they are basically doing just that. And the problem we are dealing with is that we need hundreds of thousands, millions of these computing devices. Each of the computing device can take up to as much, draw as much power as a refrigerator in your house. And so to train a model, you'll need to put in millions of refrigerators running continuously for months and months to go over all the data many, many times. And so we have to build these big warehouses full of these computers, which are known as, for lack of any other word, a data center. And but they not just have data, they also have a lot of compute. You could also call them compute center, but it's all the same. There's a lot of servers inside. Each of the servers often have 8 accelerators or GPUs. Each of the GPUs take 1 kilowatt or more. And so now you have hundreds of thousands, millions of those things. So that's why a data center needs so much power. And that's just part of the equation. They also need a lot of power for cooling. They also need a lot of power for the storage to communicate inside and outside and so on. So exactly how much energy are we talking about? So International Energy Agency, there is an agency called International Energy Agency, and they try to collect these numbers, and this is from their recent report from 2025. Y-axis is in terawatt hours, and x-axis is years. And historically, the curve was not really flat, but was not growing very rapidly. And in 2024, we were consuming, all the data centers were consuming about 300 to 400 odds terawatt hour of electricity, which happened to be 1.5% of global electricity consumption. And of course, around that time, we are seeing, we have started to see all this rapid boom of all the energy demand and all of the things that are saying, and they have made many projections. The ones that are sort of, if we go at this rate, is the base projection. And then we have high efficiency projection where if research like what we do are effective, you would be there, or maybe the demand will be even less. And then if AI faces headwinds and everybody stopped building data center or none of them get built, then it will still grow, but not as much. And then of course you have this other scenario where it's going to ramp up really, really quickly and will need even more. Nobody really knows exactly how much we need. These are all projections. Even in their report, they talk about, they collected these projections from many different projection firms, and none of them agree with each other. And so the numbers are all over the place. Nobody has any idea. But the short part of it is we need a lot of energy. In the global context, percentage-wise, even if you double from 2024 to 2030, it might not be sort of significant percentage-wise because there are other energy drawing pieces, different industries, they consume even more, but nothing is growing as fast as this. And people who are very bullish about AI, they keep talking about it will just keep growing at an exponential rate. So that's where all the worry comes. The other problem is the worries are often localized. The data centers are not small and millions in numbers that are evenly distributed across the planet. They are much fewer and concentrated. So the locations they get concentrated, they will feel significantly more effect on them than sort of the world as a whole because they are not evenly distributed throughout the world. But energy demand for AI and ML is a big concern. As you can see, the dates of these two screenshots, one is from 2024, the other is one from 2025, 8 months apart roughly. But this is one thing that everybody agrees on, that we need to make it easy for everybody to build these data centers so that we can do more AI because there are many reasons, but one of the things that I can think of, if we are not doing it, someone else will do it anyway. So we should just go ahead and try to do it. I'm not a policy person, so I don't really know like what are all the reasons, but it is happening and it's very hard to avoid talking about and thinking about AI energy consumption. And there are two approaches people are taking. One is create more power, increase energy supply. On the supply side, this has led to many problems, including US have already slowed down the plans to retire many coal-powered plants because it's more important, seemingly, to have energy than not use coal. And then also, many of these big tech companies, they are trying to get into nuclear energy because that seems more abundant energy and seems cleaner with other problems that people are having to deal with. So I lead the ML Energy Initiative, and what we are working on is however much AI we do, whether it's bullish projection or pessimistic outcome, whatever we do, we want to figure out what is the minimum energy we need to do that. It's as simple as that. Doesn't matter whether it's increasing by 100x or becoming smaller by 10x or staying steady. We should be doing things efficiently. So our main objective is to understand where is the energy going. I mentioned earlier that instead of trying to estimate, we want to precisely measure. And then we want to optimize. We want to figure out how much of this energy is actually needed and how much is wasted for no reason. And then beyond that, we want to expose trade-offs so that people can decide if I am okay with something being slightly less accurate, then I can save this much energy, and depending on your application and use cases, you may be able to make those choices, or something running fastest versus something running slightly slower may also expose and enable some trade-off. If you're okay with things running maybe 5% slower and that saves 15% more energy, maybe you'd be willing to take that solution. So we've been working on exposing all these trade-offs. And the remaining of the talks, I will try to answer these three questions. Where do the joules go? How do we reduce runtime energy bloat? Bloat is usage that actually can be taken off, but you'd still have no impact on the process that is running. And finally, after you have removed all the bloat, then if you take something off, you have to give something up, and how to navigate those trade-offs. So let's start with the first one. Where do the joules go? As I mentioned earlier, people were doing a lot of projection and estimation. They were all based on these rough estimates that different hardware vendors put out. This is numbers that I put it in a pie chart from some technical white paper from NVIDIA. These are sort of state-of-the-art AI servers. They have 8 Blackwell GPUs. And then according to NVIDIA's estimation, power provisioning for these servers would be 2/3 for the GPUs who will do all the AI computation. And the other 1/3 is for CPU and storage and networking. And then, of course, by fans, I mean cooling. Cooling didn't fit in the pie chart, so it's just fans, but some form of cooling. And you end up provisioning that way, and that's how people ended up with a lot of different numbers. But what we did is we wanted to measure, just because you provision doesn't necessarily mean you use it or can use it. So we built this tool, and we've been building it for the last 4 or 5 years by my students, actually, not me, Zeus. So Zeus provides very simple API to very precisely measure. I will not bore you with the details of the API, but I want to say somewhere in the middle you will see there is a begin window and end window. Anything that you run in the middle of the window, Zeus can very precisely measure. So if you have a code, whether it's training inference, you call Zeus and put it in. It's very simple and easy to use. And then you can see how much energy was consumed when the computation was running on the GPU. Zeus has been, at this point, very widely lauded by many different communities, including the PyTorch, that is the common sort of software people use to do AI and ML, by Mozilla, by GitHub, and from a variety of other sources. But what we did with Zeus is that we put the begin and end window around AI inference. And this is a massive plot, so I am not going to force you to go over it, but I will still give a quick rundown of what's going on. X-axis is many, many different open source models. These are top of the line model. As of a few months ago, they are not anywhere near top anymore, so we have to redo the benchmark every few months. This month, we are doing another run of the whole benchmark. If I gave the talk 3 weeks later, you would have a very different set of names because AI keeps changing very, very quickly, but the point would still hold. The y-axis is showing normalized power draw of a query when you are trying to run a query for a particular model. So what it means is that the GPU, as I said, can draw as much power as a refrigerator. But when you run a query through a particular model and it's running, it cannot really draw as much for a variety of reasons, the most important one being the task it is trying to achieve, the computation structure it may have, may stop it from actually being able to utilize all of the computation resources in a GPU. So just to get a sense, you can see all of the black bars are like somewhere around 0.5, up and down a little bit, whereas the orange bars to the right, they are closer to 1, so they can actually use all of the resources in a GPU versus the left one. What is happening is the rightmost one are image and video generation. Some of you may already have used the Sora 2 app. When you generate video, the model that you use, they are more computation heavy. Whereas many of the models on the left, these are LLMs. So for coding, for chatting, most of the ChatGPT and Claude use we do. They are on the left side. They are sort of memory bound. So they cannot effectively use all of the compute that are available. It also varies on the workload. It depends. But for the workload that we used, it didn't. And the ones that are sort of in the middle, those are multimodal vision language model and other kind of modality put together. They are a mix of compute heavy and memory heavy. And as a result, they are not as low as sort of LLMs, but they are also not as high as image generation. And they fall in the middle. The point is, without actually measuring, we cannot make a sort of general statement about how much energy does AI consume. And that's why if at the end, if in Q&A someone asks me, okay, how much does ChatGPT consume? The answer is like, I don't know. Other than OpenAI, nobody can estimate or guesstimate it because it's not just what is happening in the model that I'm showing. It's actually beyond the model. It's what is and how the system is built. In this case, the A100 on top, I'm showing it's kind of NVIDIA GPUs. At this point, they are 2 generations old. And when you change the GPU from A100 to H100, that's 1 generation older now. As I mentioned earlier, the most recent one is Blackwell. This is Hopper, H for Hopper. A was Ampere. So for Hopper, as you can see, the bars went even further down because hardware became even more energy efficient and power efficient. So for the same model, the power draw and energy consumption went down further because the hardware is more efficient. It is also affected by algorithmic choices you make. So in this particular, the 2 bars randomly I put up in the sense that they are random out of all of these models, but they are also related in that they are from the same family of model from Microsoft, Phi 3. And one is mini, the other one is small. Small is roughly 2 times bigger. The billions are the number of parameters, but small actually consumes less power and less energy is because of the architectural detail. So at the core of all of these LLM we use, there is something called attention. And depending on how the attention is implemented, how much energy you consume gets significantly affected. So it's not just the hardware, it's the algorithmic details. It's also affected by the software that you are using to run all of these things. So in this case, I'm showing again 2 image generation model, SDXL, so Stable Diffusion XL model. One is the XL version, the other one is the turbo version. In the turbo version, the image resolution of the generated images are smaller, so that's why it draws less power. So it is practically impossible without actually being present when AI is running, making any sort of claim about how much energy something is going to take. So what we've been doing is to build this ML energy leaderboard that, as I mentioned earlier, we update every few months. We basically take all of the top of the line models, then we have the workload, and then we run them on different kinds of GPUs. In the last V2 run that I presented, it was Ampere and Hopper. The current one we are running is going to be hopefully Hopper and Blackwell, and all of the sort of state-of-the-art models. So hopefully in December sometime, if you visit the website, then you will get up-to-date numbers and where things look like. And we hope to continue to do it every few months. It also requires us to actually waste a lot of energy by just running things, but someone had to do it just to know exactly what is going on, so everybody else don't have to do. So moving on, the next question is how to optimize energy consumption. So we have a tool that can measure, and we used it to measure inference energy consumption, and you put it out. But inference, honestly, actually consumes more energy. It used to be training when not many people were using AI, but as more people use AI, you train once, but then you do inference for billions and trillions of time with so many people all around the world. So inference eventually picks up. But in this case, I'm talking about training. And these are, again, estimations. I don't like estimations, but these are what we could find over the years that many different people that are listed below, they claim to estimate how much energy training GPT-3 and other different kinds of model have taken, and they go from hundreds of megawatt hour to gigawatt hour to tens of gigawatt hour. And just for comparison, to create 1 megawatt hour, US Energy Information Administration says, at least in 2022, they said you will have to burn like 1,140 pounds of coal, and then you multiply it by 21,000 or 40,000, whatever those numbers are. It's the mountain of coal or something that you have to burn. So what we wanted to do is, when we are training, do we actually need to spend all this energy, and how can we sort of figure out and optimize? And so I'm going to give 10,000 foot, perhaps even higher level view of what is actually going on when we say a model is being trained. And I tried to make it as simple as possible. I believe it will be understandable to most of you. So this is needed background to understand like how we are going to reduce. So back in the days, models used to be small. And back in the days, by that, like maybe 5-7 years ago. And you have a small amount of data. And I mean, even today, many of you who are active researcher and using AI and you are training, you probably can train all these things in your own computer in the lab or in a single server. So you have a GPU, you have some data. As I said, it's the same thing, data and compute. You just go many times round and round, and you end up with a trained model. As time went by, people figured out that, okay, we need more data to make the models better. So then we introduced something called data parallelism. The data got bigger. Our models are still the same, so we just got in more GPUs and put the same model in each of the GPU, but we divided the data. That's where data parallelism comes from. Data has been parallelized, model is still the same. And then we do the same process. Ignore the all reduced part. It basically says that after each of the GPUs do computation separately, we need to aggregate them so that they all have similar worldview, and then we do another iteration and we do thousands and thousands of them. And then time went on, then we went into this new world where models got larger. a single GPU cannot hold a model anymore. They are sort of going out of the GPU. So what we ended up doing is that, okay, we know how to divide the data. We need to figure out how to divide the model. So what we ended up with is something called model parallelism. So we have data parallelism, data is divided. Model parallelism, as the name suggests, divide the model. And now they are across all of these multiple GPUs, and each of them are working on small amount of data, one batch. And then if we want to go one GPU at a time, we'll end up with the other GPUs waiting, like the other GPUs that follows waiting. So what we did is something called doing work in a pipeline. So when stage one is done, working on small piece of data from a micro batch that is given to stage one, and stage zero start working on the second one. So everybody is doing some work, and then we end up sort of finishing the training, and we have a trained model. Whatever the model is, at a very high level, they are doing some variation of what I just said. The data parallelism and model parallelism, no matter how sophisticated and how magical the model feels, they are doing just this. And so this is where it's going to get a little bit technical, but I wanted to give people a taste of like what is actually going on. So you remember the figure? We divided the model into 4 parts, and I call them stages. Now I'm going to explain the stages. Stages are a model, and a portion of the model is in a particular device, and we are calling it a stage. We divided the model in our example into 4 parts. X-axis is time, and each of the row is a particular GPU where the stage is located. And each of the boxes that you see, these are computation. So the way modern neural network works at its core, it's based on something called back propagation. So first you do forward computation through all of the stages, then you have to do backward computation through the whole network again, and then you keep doing this back and forth on all the data that you get practically forever, or like at least days and weeks, then you end up with trained model. I am not an AI expert, so I can't explain how it ends up being, converging to something that is useful, but I'm talking about the physical process that happens. So the reason we called it pipeline parallelism, as you can see, F1 appears in all of the stages, but after the previous stage have finished. And then if you follow F1, it goes to next stage and goes to stage 4th one. After everybody has finished the forward, then the backward starts. So B1 can only start after all F1 has finished. And then after the bottommost row finishes B1, you can follow all the B1s one after another going upwards. And it's true for all of them. And the reason the numbers go up to 8, you can see on the right-hand side we have B8. That means we also had an F8. Because in our example, we had 8 sort of micro batches. So the batch was divided into 8 micro batches. And we are doing one small piece of data that are going through all the stages, forward, backward, forward, backward. All good. This is just a drawing. But this is the same drawing at scale. So this is something, GPT-3 is the precursor to ChatGPT from 6-7 years ago. After that point, they stopped talking about what their models look like, because I think then they figure out there's a lot of money to be made. But we ran GPT-3 on actual NVIDIA GPUs, and we now sort of drawn the same figure at scale. So you remember we have the tool that can measure how much power is being consumed. So what we did is we used the tool. And so what you can see, the colors are showing the power draw in steady state when these computations are happening. The bar at the top, it goes from 0 to 300 because that's the maximum power range of Ampere A100 GPU for the particular version that we had. And all of the boxes are almost always closer to these orangish red because they are all drawing close to the full sort of power draw almost all of the time. And now this is something we are all familiar with, the critical path of computation. Many of us have done a lot of projects in groups. And then there is one person who is always late. And then when the project is going to finish, we often have to depend on that particular person finishing, because everybody could be done, but that one is still not done. And then we have to wait. That's a very simplified version of the problem with critical path, but that's what it is. In this computation, for us to go from the leftmost side to the rightmost side, this sequence of computation under the blue line, all of them have to finish. And then, only then, at the very end, we will have like the whole computation of an iteration is finished. So these are the ones that are critical. If we slow them down, what's going to happen? We will slow down the whole thing. Someone who are relying on, they are already slow and they dictate how long something is going to take. If they get sick for one day, the project will be delayed by one day because they are not around. And I mean, in this example, nobody can do their work, so you have to wait for them. So what we observed is that pick any random sort of pairs of nodes or anywhere, you see there are computation and there are white parts. So in the white part, they are white because nothing is running. The GPUs are sitting doing nothing. It's true for all of us. When we do project together, we are waiting on somebody. We are, I don't know, playing games, watching movie because, I mean, nothing is happening anyway, and we are bored. So what we did is, in our lab, we created an algorithm that will figure out, of all of these parts that are available, how can we reduce their power draw, everybody outside the critical path. So they all actually became slower, and they filled up some of these empty spaces, and they could only be slowed down up to the point when they themselves don't become the bottleneck. Like, I can relax because someone is slow, but if I relax too much, then they might be done, and then they will, I don't know, call me that, okay, now we are waiting on you. So everybody can slow down, but not slower than the slowest part. So we built an algorithm that automatically figures these things out, and other than the critical path, we set frequency of GPUs at precise points in time. And thing that we have done, as you can see, the critical path is still fixed. So the total time you take doesn't change at all, but you actually end up saving a lot of energy because all of this computation are now, instead of drawing 300 watt, they are drawing 200 watts or like close to 150 watt and so on. So all of these actually adds up because we are talking about 100,000 GPU doing the same thing. And other than 1/4 of them, everybody else are basically doing, I don't know, less work, or at least drawing less energy. They are using the extra time they had, but they are running at low power instead of running at full speed, because finishing early has no benefit. It's complete just waste of energy. So that is the intrinsic bloat, but the other source of bloat that we call extrinsic bloat is that sometimes there are multiple pipelines that have to be run. I introduced data parallelism before. So each pipeline is a data parallel copy. And I mentioned, don't worry about it, they just have to synchronize. But now we have to worry about them. They do have to synchronize. We cannot move without them synchronizing. So what happens is, if one of these pipelines becomes slow, all the other pipelines, them finishing earlier has no value, because the slowest pipeline is going to dictate. So again, you get the same set of opportunities that I mentioned earlier, and you can, I don't know, find these things that are external to a pipeline, giving you opportunity to run at a slower pace, because again, finishing fast has no benefit. So what we ended up doing is finding this time energy frontier, where essentially what we showed, that what happens typically today, that you run all computation at the same speed and you consume some energy, but instead of doing that, if you reduce the intrinsic bloats, you can cut a lot of energy consumption without moving at all in the x-axis, the time domain. And then if there are stragglers and someone is actually slower in time, they are somewhere over there in time axis, you can slow down everybody else other than whoever is already very slow, then you can save a lot more energy. And so by eliminating both intrinsic and extrinsic bloat, we can sort of save a lot of energy. The problem is NP-hard. I'm not going to bore you with like how we are going to, I don't know, solve it. We did solve it, but at a very high level, it's a graph cut based solution. It's like ignore it. But the solution is interesting in that you have to start from the opposite end for a solution. You have to start running things as slow as possible. Then you only speed things up that by a little, that saves some time and reduces a little bit energy, and you end up drawing this whole frontier. That's like at a very high level. So even though it seemed like we are at the left side where things are, but the algorithm has to run from the right hand side, and the details doesn't really matter. But what we did is that we made the algorithm implementation as an optimizer in Zeus. So anybody who is training, they can actually take it and use it. And most recently, we have been collaborating with NVIDIA to integrate this type of optimizer in the very large scale training that many different companies like OpenAI and Anthropic do. And it leads to 13 to 29% energy bloat reduction across multiple types of GPU. Depending on the GPU, you can get more or less. But like even 1% of, think of a 1 gigawatt capacity data center is 10 megawatt, 10% is 100 megawatt, and so on. So even a few percentage point improvement is massive savings in terms of cost and how much energy they need for the data center to be provisioned and so on. There are a bunch of numbers, we can ignore that, but essentially it's a very promising project that I'm very excited about, and we are doing many follow-ups where we are trying to go even deeper inside and look into sort of in each of the F and B boxes that I showed. We can look inside, and what we have found, my students currently are actually running experiments. Initial results say we can save about 10% more, close to 10% more, optimizing individual boxes at a very small scale. So we can save even more than whatever we found so far. And the third piece I will go over very quickly, but earlier I mentioned that this performance, energy performance trade-offs, what it means is that when you are trying to train a model, typically you have an accuracy target that you want model to be, at least as accurate as some target you have. And so you can define a metric that we define what we call energy to accuracy. How much energy would it consume for a model you are training to get to a target accuracy? This is very similar to how traditionally people have done, where they have talked about time to accuracy. To reach a particular target accuracy, how much time will it take? We wanted to measure instead energy to accuracy. And what you can see, energy to accuracy is essentially time to accuracy multiplied by the average power, because watt is joule per second and second is second. So when you multiply those two things, you get joules, the energy. And then time to accuracy, the total time it will take, is how many epoch iterations you have run and how long each iteration take. You multiply them, you can get total time. You multiply that with average power, you get total energy. It's as simple as that. But the interesting part is that we found two hyperparameters that affect these three different things that I highlighted. So the batch size, earlier in the example, I had a batch size that we give some amount of data. So batch size dictates how much data in every iteration you are going to put in when you are training. It affects how long an epoch takes, more data, longer epochs, and also how much power on average things draws. And power limit is the maximum power limit of a GPU. I showed earlier for A100 in our example, it went from 0 to 300, but it has knobs where you can set never cross 200, never cross 250. So that is the power limit that you can control. That affects also average power and epoch time. And we also found that from a machine learning point of view, the batch size affects how the model actually gets trained and its convergence. So what happens together is that if you try out all possible batch size and power limit combination, which we did in the plot shown here, you get many of these points that have different time it took to reach a target accuracy and different amount of energy it took to reach that particular accuracy. The triangle is for any given model, whoever created the model and trained the model, oftentimes they put up on GitHub and they say, okay, these are the hyperparameter we used. The default for this particular model is shown in a triangle. And as you can see, there are many, many configurations that are better than the default choices of parameter, both in x-axis and y-axis, both in terms of time and energy. So that means if you see a model and you want to use it and you download it and you want to train it locally, you should think about how you are going to train it instead of just downloading and start running. That may not be energy efficient nor time efficient. And all of these points at the left bottom that you can see, these are on the frontier. So they form a frontier, which is the Pareto front of all of this model, where you have to give up some time to save energy, or you have to give up some energy to reduce time. You cannot get for free anymore. Points that are inside, you can win in both directions. Points on the Pareto front, of course, you have to give some to get some. And now the plot that I'm showing, we drew it by, again, burning a lot of energy by trying all possible combination. In reality, you don't want to try out all of these configurations. So what we did is, depending on what you care about, how much you care about time and how much you care about energy, we actually created a cost function and an algorithm to search effectively. So instead of trying all possible choices, you can get to sort of a good solution on the Pareto front very quickly using sort of our algorithm. And I'm not going to give the details of the algorithm, but essentially what we do is, it's a multi-arm bandit formulation. So it's a way we basically search it out given this cost function. And what we found is that visually what it looks like, the grid search would be exhaustively trying all of these squares, whereas what our search algorithm does is jumps around and only tries out few of the choices and get to the same solution or very close to it without having to exhaustively try out all possible combination. So what you end up having is that, well, Zeus and grid search are often the same thing. Sometimes Zeus also happens to find better solution. But essentially, y-axis here is energy to accuracy for variety of models. The default line is at 1.0 if you just downloaded and used whatever the author said without doing any optimization. You could actually end up wasting like 15 to 76% more energy. So by choosing the right hyperparameters for training, you can, again, save a lot of energy. So this is all the discussion that I'm talking about here is for training, but for inference, similar choices exist, because when you are trying to generate an answer, there are many, many models that perhaps can do the same thing, but they have different accuracy and different energy consumption. And you could plot all of them in similar scatter plot. Instead of time, you would have accuracy versus energy, and then you'd still find a Pareto frontier. Then you'd have to make a choice that, okay, how much accuracy do I need? And for that accuracy, what is the lowest energy model I need to use? We don't need to bring out the, biggest hammer for the smallest problem. We need to find appropriate hammer for the problem that we have, and that way we can sort of save a lot of energy. So this is by very carefully thinking through, and the reason we are building all of those things with my students is to make these things available as completely open source and free to use, and is very well documented library that people can try out. And my students would be more than happy to, if you run into an issue, file an issue on GitHub, and they'd be more than happy to address. So these are PhD students. Some of them have already graduated. Many other students, undergrad and masters, who are working on it or have worked on it in the past. The project is primarily led by my superstar student J1. He has been sort of carrying all of this hard work carrying on, and I'm just going around giving talks and claiming a lot of credits. What we have found in the process of doing all these things, and these are some of the two takeaways I want people to have. One is, whatever numbers you see, and there's a lot of articles and everybody wants to talk about it because this is a hot topic, all numbers are not necessarily equal. Some of them are estimated, some of them are guesstimated, some of them are completely made up, and very few are actually measured. And the things we should care about are number that we can see and measure, and not pessimistic or optimistic estimation, because that allows for people with different agenda to pick one point or the other and to make their own case that it has no energy consumption or it is going to kill everything. The truth is often in the middle and depends on workload and model and hardware setup and software stack and so on. The other part is just because we are running things and we are spending energy, they are not, all of them are not doing useful work. A lot of energy are being spent that are essentially bloat, and you can trim them, and your model will still have the same accuracy, it would still run at the same time. And I mean, we are basically just throwing energy into ether. And what we should be doing is think of at every step, what is the minimum energy we can spend to get the same task done. I think it applies for us individually as well now. All of us want to find what is the shortest path to getting something done instead of like wasting time and energy. Same goes for the model. Currently, we are at an exploration phase, so people are more concerned about adding new functionality. But I think as sort of we reach a point where the capabilities are somewhat well understood, we will see more and more interest and effort like ours that will try to figure out what is the minimum energy we need. And so that leads to some of the biggest challenges that I think that we have in terms of going toward energy optimal AI systems. And of course, I said energy optimal AI, but we need to think about the systems, because how much energy AI will consume depends heavily on everything around it, sometimes more so than the model or data. So I believe what we need to understand, what is the energy scaling law. Many of you have heard about scaling law, which says that the more data you have, the bigger model you need, the bigger model you need, the more data you need, and so on and so forth. But what we need to figure out, how much energy we need to spend to get to a particular sort of level of accuracy for a model and having a better understanding of it so we can use it effectively. We want to be able to understand, say it takes energy, and right now we can measure. Why is it taking so much energy? I just said, okay, it does. But why so? So we want to be able to debug and figure out what is the root cause of this energy consumption. Is it software? Is it hardware? Should I have used different algorithms? Should I have tried different type of attention implementation and so on? Different optimizer? We should be able to debug easily. And then finally, we need a lot of research at the hardware level. Many of the things we actually could do are not possible often because hardware doesn't provide that feature, it doesn't have that capability. And as new generations of hardware are coming out, they are adding more and more such features and capability that will allow us to extract more efficiency. And hopefully, I don't know, if I get to give this talk in a few years, I will have even more savings to share. And by then, we'll have much better understanding of how far we are from energy optimal AI. With that, I would end, and I would be happy to take questions. Thank you. I was told to bring to this slide.
So oh. Good evening. Firstly, thanks for the talk. I learned a lot. I think I remember you talking in the chat about how there's even more energy being consumed on like the AI inference versus the AI training side.
Yeah.
I'd be curious to know, like, as someone who's very much interested in this, what are some resources I could go to maybe like investigate this more, to understand exactly what the level of energy consumption is on the inference side versus training side, and maybe in the future how it could be addressed?
That's a very good question. So the resource, of course, I would say go to ml.energy. That's the URL. There are no reliable actual measurements of training energy consumption, because none of the big companies that are training, they actually publish how much energy it took to train such a model. And to be fair to them, it's also very hard to actually give you a number, because whether you should be giving, okay, this is the last run that we are actually running, versus like 1,000 other things we tried, none of them worked as well. And so it's very hard to add them together. Then the number will look very big, but Many of the things they had to do trial and error, so it's very difficult. Training, we also don't have a number because we don't have enough resources to try to train a model to get a number. Inference, we can run and get numbers as I have, and as I said, we'll be updating the leaderboard in a month or so with the more up-to-date, like including GPT-OSS and Qwen 3 and all the other new DeepSeek R1 and so on, all the other newer models that are coming up, many out of China, some from US, and we'll be updating. And so that is a good resource to look at, like how much inference consume. That also is not a complete answer, because that will only tell you an average query how much it takes. But when you are serving something and say someone is building a big data center, they are providing a service to millions of people, and how much in total is going to consume depends on how many people are using it, how many queries they are sending. So it's very difficult to get sort of this macro scale number. Micro level, we are measuring and training. We can try to do small scale training and measure. In the third piece, we did train small models on single GPUs because that's all we can afford. But otherwise, it's very difficult to get hold of actual measurements and numbers.
All right, thank you very much.
So any other questions?
Non-engineering question, but thank you for making it so understandable for those of us who are not engineers. So I come at it from the energy sector, where we know, from a sustainability sector, where we know how we can present individuals with information about their energy use to reduce it.
Mm-hmm.
So we have various strategies we can do that. But it does require having some measurement of the energy that's being used and to compare it to, for example, other users or strategies that users could pursue in order to minimize their energy use.
Yeah.
I've heard Harvard is working on such a tool, or somebody at Harvard is working on something that could be, let's say, go on ChatGPT and you could see how much energy your searches are using as a user. But listening to your talk, I'm wondering how feasible something like that truly is, and how I mean, I guess maybe you could get into the ballpark, but that's probably about it. But I'd love to hear if you're working on something like that, or is it feasible, et cetera. Thank you.
So you cannot do ChatGPT unless they are working with OpenAI. They cannot. So you need access to the actual hardware and where the query is running. But the tools that we have built, if OpenAI is running these tools, they could, in theory, show exactly how much this query took. And then you said, sounds good, how much that took. And then, oh, can you go back and change? Like, we could do like every single step, because we can measure at a very fine granularity at millisecond scale. And so you could get those numbers. And even our numbers are still estimation, because what I didn't go into the details of is that you can go even finer grained and get more numbers. So for that kind of tool, they could at best do, first they have to make a guess. What does these OpenAI, whatever model it went to, it looks like? And then they could try to find a proxy in the open source world. Then they could run it in that model. Then they could use our tool to measure. Then they could say, okay, if OpenAI is using that and that is similar to this, and then that will happen.
And that'll use more energy.
That will use energy. Because like for every query, you need to run another query. Then you can, build up another trainer model that will try to do that for you instead of running it. Maybe analytical model or a machine learning model, but it's very difficult, honestly, to get accurate sense of things. Because most recently, one of my students brought this to my attention, French government, they have created some website, it's in French, so he used ChatGPT to translate it, but essentially there it shows, okay, you do this query and you give query to their website, and it runs on Anthropic and OpenAI and whatever, then they can say, okay, how much energy it consumes. It's impossible, because they have no idea exactly what, where, whatever OpenAI, Cloud, or anybody else is doing. So there is this cottage industry of everybody claiming that they can estimate and know and guesstimate. As far as I'm concerned, from a scientific point of view, they are at best estimate, at worst it's just complete made up numbers. But yeah, that's where things are. So We have, say for example, Google recently published some numbers in August about how much energy and water consumption of their Gemini Pro model. So before releasing the white paper, they came and talked to us, like, because we do these measurements, and we discussed like this and that and how they measure. They have different hardware, so we don't really know how their hardware actually works. But at the workload level, assuming their hardware has similar efficiency to the GPUs that we run on, that you can buy, it sounded okay, but still, and then there's a lot of journalists reached out to us and asked questions like, okay, is it like correct, that is it believable? The answer is like, I don't know. I mean, at a very high level, if I were to guess, and I know some of those researchers, they sound reputable, so they are not completely making things up, but no one really knows exactly what it is, and they also only give a median number, and not really like the distribution of all the queries. And so it's very hard to tell like what is the average or how far the worst ones are. Maybe median is skewed. And so it's very hard to know without you running a service. Yeah, so thank you. Yeah.
Thank you for this. It's really helpful. Another very much non-engineering person here. I came here hoping to be a bit reassured, and I've been reading the same kind of news that you had in the first few slides. And I'm really grateful for the work you're doing, and I want to ask, as a fellow U of M employee, what I understand you're not in the policy realm, but what are some things that we can tell our students? What can we hope for, ask for, that you think would help as a community to address some of these questions? Because it sounds to me like we don't even have an accurate sense of our own usage. So I have some students in my class who just refuse to do any of the assignments that we're asking them to do with AI. I want to train them to work knowledgeably, and part of that knowledge is how to also reduce the footprint as much as possible. So what are some things that you would advise us as fellow U of M people in the U of M community?
Yeah, thank you for the question. It's, as you can imagine, very hard to answer, because like I'm not an expert on any of the things that requires, I don't know, I need knowledge of to answer that. But I think if we were running some AI models ourselves, and then students were using those models, and then we could have a very good estimation, and we could have these type of tools running, and every query they do, you would see the numbers. Actually, I mean, at some point, me and my students, we did used to run a live service where you could give a query and you'd get an answer, but with the answer, you'd also get exactly how many joules. So we had that tool built up more than 2 years ago. So if you go to ml.energy/leaderboard, there is a tab called Colosseum in there, ml.energy/leaderboard. You go to the page, there's many tabs, these and that. Toward the right bottom somewhere, or like, I mean, the top row of things, there's a thing called Colosseum. It's offline now, but there is a YouTube video that my student put up, because we don't have the money to keep it running. But essentially, you could give a live query, and we would be running on an open source model, and we would be measuring exactly how many, energy it consumed. And then you would know it's more or less, by doing some translation. So if we were running our local things, then we could measure, and then student could decide this versus that. The problem is, like many of these open source models, they're getting better. Oftentimes, they are still not, say, as good as like all of these for-profit companies, because they put in a lot of resource and fine-tuning and post-training that open source models don't really, not necessarily go through. But that would be one way. Like if we were running this, UM has UMGPT, and I think maybe we do try to run some of local models. I haven't really used myself, so I don't really know exactly what we have. But if we were running, or as part of your course or something, or as a college, school, they were running, okay, these are the servers, these are the models we have accessible to the students. Whenever they give a query runs, model produces output. It also gives, some energy number, which we can actually reliably measure if it's running on NVIDIA GPUs or other kind of GPUs. Then that could be useful, but that needs a lot of, effort and time and resources. And initially, when we built it up, that Colosseum, if any of you eventually end up on that YouTube video, we wanted to actually measure. Everybody says they, love the earth and save energy and whatever, but exactly how much do they care? So the interface was such that you'd give a query, it will go to 2 different models, and then you will get 2 responses. We are wasting energy, I know. Then you will get the results, then you have to pick which result you like more. And there are many such websites. But then we would also show you how much energy went into answers. And then we would ask you, now do you want to switch the choice you just made? Like say something is consuming 2x more energy, and do you want to switch back to that one, or do you want to stick with this one? Is the 2x better? And we wanted to do that study at scale. And unfortunately, we ran out of resources. We couldn't find interest. Like when we were doing it, people still didn't figure out energy is going to be a big deal in summer 2023. So we were also too early. And also we didn't have enough money to keep running GPUs and just allowing people to do 2 requests for 1 query. But that type of infrastructure would lead to very interesting studies, not just like understanding energy, but like the problem that you are dealing with. Just to understand what is the break-even point where people will say, okay, this is like too much energy to waste for this response, I don't even care. No? And so we could have a better understanding. How to enforce it would be another problem. Like before query starts running, how would you know which one to select, because you know they would like the answer or they would think it's a reasonable answer. So there's a lot of research problems to solve. That's all I can say. I know I didn't give really an answer, but there are many, many different ways to go about it.
Thanks. I have maybe it's a comment more than a specific question about this conversation of energy consumption and is it too much and what is too much and things like that. Look, there is the issue right now that there is a whole bunch of money investment pouring into this AI companies and they have free money essentially to burn. And that's what's happening in terms of all of the growth. So there's already discussions right now happening, as this year is coming to an end, that maybe this party is going to come to an end. Maybe it's not sustainable, all of the growth, and hence all of the growth projections. That's happening. So now some of the usage that you are seeing is subsidized, right? I can go to Gemini or ChatGPT or whatever, submit a query, and there's no charge, unless I'm using one of their superior models and I'm paying for that, and even that is subsidized. So maybe it comes to a point when now it's expensive to run these queries, and automatically that limits the amount that you might be willing to do it or what you're going to now use that for. So maybe there is a self-correction mechanism that comes through. Of course, there's going to be research on how to make it more efficient and do that. I mean, that's one of the things that DeepSeek models were lauded for, in terms of them costing much less to produce than what OpenAI and all of these guys
for that kind
are
of
doing.
model, that's what I was telling earlier. When you say, okay, how much it costed to train and how much energy, is the question is, what are you reporting? Are you reporting that, okay, this is the final run, or are you reporting, okay, I tried 1,000 other things, I'm not talking about them, or I used someone else's pre-trained model and learned from that, and so you are getting all of those energy and cost for free. So there's a lot of nuances to figure out. But I agree with you. I personally feel like, that, like you said, is extremely, heavily subsidized, and eventually they will have to make money and profit, and then they will either become extremely efficient or charge more, and then some people will walk away. The risk there, what I have heard from some of my other friends, especially in non-engineering, in sort of social science and others, is that will also create bigger divide between people with money and people without money. Now people with money, they will pay and they will use AI and do things faster, and maybe you and I will be just trying to type things up and take 3 days to do the same thing, and then we'll fall further behind. And so it's sort of difficult, but I think the solution to me, and not just because I do efficiency, but I do efficiency because of the same reason, is that no matter what you do, small or big, you just want to figure out what is the minimum thing I need to do to get this thing done. Anything else should be, shaved off, and we should try to, make it as lean as possible. So that is always valuable. The bigger picture is too big to figure out like how it's going to play out at the global economy level, because I think there is a valid concern that at least there are multiple different players that are all trying to get better, and no one really knows where the end is, and so it's very hard to give up before others have given up, and so everybody has to keep trying.
Yeah, so thank you so much for the talk. I might have two questions if I can divide it. So the first thing is, you mentioned about different sizes of hammers to solve different kinds of problems. Given that we have these like big tools doing a wide variety of problems, let's say in image generation or some sort of text models, how big are these models, let's say, going to be the biggest hammers? Because if they are solving a problem to a certain efficiency, it probably meets all of our requirements. Do we need such larger models, or what's the future of this energy demand going? And the second question being, are you partnering with any data centers or cloud service platforms to understand how the behavior is changing, or it's dynamic or not? Yep.
That's a very good question. So for the first one, so there is a trend in general that people are feeling that for all queries you don't need the biggest hammer and the biggest model. So you might have seen with GPT-5, they also mentioned they have a router which basically first sees your query and then tries to route it to the right model that will satisfy, and they expect that you will be happy with that answer and you don't need to go to the bigger one. And similarly, if I know your query is generate an image, no need to send it to the text generation or like the bigger thing, just send it to an image generating model. So as I said that, we think ChatGPT is a model, but it's actually a system of systems of models, and so it's a giant graph of many things. I don't know what they do, but that's what I would guess, because it doesn't make sense to throw high to like the biggest thing. And then versus like someone may have like 3-page description of a very complicated unsolvable theorem and say, okay, now solve it. It will still give it a try, probably will fail, but so there are ways, and many people also have said that maybe we should focus on small language models instead of large language models and figure out like what is the smallest version that can do it. So there are people who are working on and trying to figure out how to best organize this variety of different models so we can get the most out of them without having to always go for the biggest hammer on the shelf. For the second one, we are trying to, more recently we've been trying to, some of other researchers, not data center operators, like who deal with grid and and microgrids and how those get affected by data centers. One of the problems that I didn't mention is becoming a big deal nowadays is that when training happens, I said at every end of every iteration there is a synchronization. So when synchronization happening, these 100,000 GPU or however many you have, they all fall in terms of their power draw, because communication takes much less. But it's not 1, not 10, not 100, it's like 100,000. And then in a few milliseconds, tens of milliseconds, they sort of all swing back up to the peak. And this going from very high tens of megawatts to close to zero, and then going up, this actually causes grid level stability problems. And there was a recent paper by OpenAI and NVIDIA and Microsoft where they analyzed, because we don't have access to the data center, so we can't, but they have analyzed these things and they have proposed different kind of solution. NVIDIA has hardware solution, there are software solution people are working on. We are also trying to work on that type of solution, what you can do in software level, because if you know what is happening during a training, you could better design. You don't have to consider data center is an opaque box. If you go in and know, okay, we are doing training and inference and this is exactly what they look like I broke it down to the level of like sub-second blocks, you can go further down even. As I said, my students are working on like looking inside each of these small blocks. And so you can do a lot of this optimization, but getting to work with any of these large operators is very hard because all of them are very secretive. It's not just OpenAI, everybody is closed AI. And everybody is very secretive of their operation and what they are doing, because everybody feels that this is their biggest opportunity to make money ever. And so everybody feels like they will be the one ahead of everybody else. And so there are very little knowledge that are available outside.
I had a question just tying the beginning of your presentation with kind of the end or middle. I was struck by the pie chart that has the GPU, the CPU, and the fan, and just how much more the GPU was than the CPU. And then hearing the presentation and the strategy of gaining efficiency by slowing down things that were off the critical path. I don't know much about GPUs and CPUs, but is it possible that maybe we don't need so many GPUs with a CPU? I don't know if a CPU is just slower, but are we overbuilding in some way?
Yeah, so it's a very good question. The problem is CPUs are very slow. So, I mean, in comparison to GPUs, of course, we have done forever everything. Even in my laptop, I don't have a GPU. I mean, I'm like writing all these papers on that laptop. But the computation these AI models have to do, they are massive matrix operations. And so GPUs are basically very good at doing that type of operations. CPUs are actually better in some of the more complicated ones, but AI operations are often just same thing over and over again at very large scale. So GPUs are much more efficient. And in fact, I mean, GPUs are energy efficient as well, in the sense that to do the same amount of computation with the CPU, you may end up actually spending even more energy, not just time, but energy. So the energy part is power over time. So GPU has high power, but then it will run quickly and the time will be smaller. Whereas CPU would have low power, but will run forever. So on the aggregate, the total area, which is energy, will end up becoming often larger in CPU, many times larger. So it doesn't make sense to do it. So some people are trying to do inference on CPU in their local machines. So that's basically, you have trained a model, and then there are many techniques, which is one common one is quantization. So you sort of cut the model and shrink it by half, or by 4x, 8x, whatever, but you lose precision, and as a result, you lose accuracy. And some people are trying to figure out, okay, how much quantization can I do while it's still somewhat usable and still runs on CPU? I mean, they are like okay, but then when you actually want to use it, many of them may not be as good as you want them to be. So we are not there yet, but as I mentioned earlier for someone else's question, there's a lot of work on, in general, small language models or collection of models. And so we have a chance to get there that will, I don't know, may improve things.
I just have a really small question. So for this method of analyzing energy usage, can you also use it on like, instead of AI, but also on other computational heavy or tasks that requires high GPU?
This is a fantastic question. I know in the example that I had, I wrote down a comment, much AI, but it could be much anything. Anything that's run on a GPU, we can measure. Anything that runs on a CPU, we can measure. Our measurements accuracy depends on the hardware counters that the hardware vendors provide. So if their counters are not very accurate, then our measurement will also not be, as accurate. Some different hardware providers have different levels of accuracy claims. Some of these hardwares have been verified by other groups with actual oscilloscope and power meter, just to see whatever the number comes out from the counter and what you actually measure by physically doing it, like whether they match, and they claimed is like within 5-10% of what the counters say. And NVIDIA actually claimed similar number. They didn't just say, okay, it's like exactly the same. They also said there might be 5% off or something. But that's all we have. But yeah, so that's basically what I can say about the numbers. I'm sorry. The other part of the question is like, what other? So of course, you can do anything on GPU. One of the things, like one of my colleagues in our department, he works in databases. So in the databases community, there is a lot of work going on nowadays, how to run databases on GPUs, because GPUs are faster. And so he and his students, they've been using our tools, to the same tool that I described, Zeus, but to measure this GPU database energy consumption. I have another colleague, he works on security and other things, and he runs different security protocol and trying to implement them on GPUs. So he has measured those things on GPU using our tool. So it is like, has nothing to necessarily do with AI. The measurement part, we just happen to apply for AI because that's the workload we care about. but other people are applying to other things. Like for example, I don't know, if you do Bitcoin mining, you can also throw it around and see like how much that is consuming.
Cool. I have two questions. First is kind of small one. Is like, how does energy efficiency compare if like, because these days there's a lot of like cloud, like things that you can do on the cloud, like Google Colab and stuff like that, training. So how is the efficiency of that compared to like training it locally? And the second question is like, I know that like training AI, like it also has a lot of water usage because like you have to cool the GPUs. So I'm curious if you've like, any of your students in your lab have explored like that aspect of it.
Thank you. Those are very good two questions. The first one is hard to answer because it depends on what model you are training, whether you can possibly even train it locally, and then sort of what kind of GPU you have versus whatever Google have in their Colab, like is it TPU, is it GPU, or whatever else. So it depends on too many factors. It's very hard to tell, honestly. The second one, the water one, water is much harder to measure because for energy you can get some hardware counters where they can, like, because they had drawing power, they get some, I don't know, some values of how much power, but water is like away from like where the action is happening. You do this computation, then GPU gets hot, then you have to cool them, and then you have, I don't know, whatever cooling solution, liquid cooling and other types of cooling, or like moving air and other things. Then they will be routed throughout the, I don't know, physical landscape. Then they will go to the cooling tower or whatever of the data center scale. And so the only water numbers that are available are from some of these sustainability reports. Some of these big techs, I don't know, have to publish, or I don't know whether they have to, but they do publish. And they talk about this is how much water and whatever consumption. So there are some works that have talked about these and that, but those are sort of these many levels obfuscated, then like dividing by many numbers trying to estimate. In fact, even in the Google's report that I mentioned earlier, they also talk about water, and they actually describe how they did it is basically what I just described. That is like far away, and so they go back and go outside the data center and took a entire like time span, how many queries ran and how much water was consumed, then divide by these and that, and approximately some, and I think their claim was like 1 teaspoon or 5 teaspoons something for average query or median query. Water is much harder. Regarding how much water is used, it also is for cooling depends on whether it's sort of open loop or closed loop system, and that affects things. I'm not an expert on any of them, but what I hear is that closed loop has much less water wastage, and most of the modern data centers are like that, both not necessarily for environment or anything, it's just more cost effective and efficient, as simple as that. So that's all I can say. We haven't done anything with water because we try to, I don't know, as close as possible to things we can directly measure, and not, because the further you go, the more assumptions you have to make, and then it becomes more and more, okay, that part is missing, so how do you guesstimate that, and becomes basically a guessing game, and it's very hard. Other than, I mean, at least according to Google, I read their white paper, it seems they also don't have any easy way of measuring, because it's just a whole data center takes this much. Exactly knowing how much anybody took live, like we can measure at millisecond level energy, because you can see power draw of GPU over time at 100 millisecond granularity for NVIDIA GPUs. So you could go up to that level. Water is like impossible. You wait for a month or year, then you divide by big numbers and you say, okay, this is how much on average.
All right, thank you.
Thank you very much. I really like the illustration you had there. So without actually knowing how GPU works, I think one question I have is when you are showing how you slow down and reduce the power consumption in each tiny unit, I'm coming from EV charging world, so I would think, okay, we slow charge, we end up still consume the same amount of energy, but we expand the time, but reduce the power. So I'm curious, like, how does this effect actually looks like? To me, you are reduce the power consumption, but not necessarily reduce energy consumption if you have to spend more time doing the computation or slow it down. So how does the effect of reducing energy actually show up in your
that's
work?
a fantastic question. So essentially, like, I didn't go into the technical details. What happens is that what you said would have been true if the GPUs were power proportional. Like the modern GPUs and hardware folks, like our computer architecture folks, they've been trying forever. They still haven't managed to create power proportional where sort of it goes on a straight line. As you increase time, I don't know, time and energy, I don't know, it's just linearly related. So they end up having this type of sort of a curve. And what we get is on two corners of the curve where for small change in one axis, you get bigger change in another axis. That's why you can actually save. So in our paper, we go into that, okay, you can slow down, but if you slow down a little bit more, then you will actually consume more energy. And so you don't want to, because like the area will get larger. And so we actually precisely find up to how much you can slow down to reduce energy, but at the same time also not slow down in terms of time so that it becomes a critical path. And so we consider all of those things, then we find it. But the root cause is the absence of power proportionality in this type of computing devices.
Hello. My question is related to how would you frame the problem between designing like an efficient algorithm versus one that consumes less energy, I guess? Because when you're talking about slowing down parts of the model, in my mind, it's like, oh, this was like wasted time, so it could have been like used more efficiently, if that makes sense. Like, or how much of a difference is between those two problems?
Yeah, so what you said would be true if we are running on a single GPU. What we are relying on is that the models have gotten so large they don't fit in a single GPU. They have to be distributed across multiple. And it's just that because of dependency between computation, not all of them always have useful things to do. You can only do certain computation when all the requirements have been met and like all the sort of preceding computations have already computed, because your computation depends on output of other computation. That's why you end up with all of those empty spaces where you have nothing to do. If all your computation were like a chain in a sequence, then you slow anything down that will affect all the subsequent things there. But because of this pipeline nature and distributed training, you end up with this opportunity. That would vanish basically when you go to single. So that's why when I was talking about every iteration level savings, I was talking about this large model. But the third part, when I'm talking about end-to-end training time, energy to accuracy, time to accuracy, they were for the whole model's entire training process. That applies to small and big model. But the second part doesn't apply to small model, because small model doesn't have to be divided and distributed where you'd get these opportunities.
Great. So should we?
Let's give another round of applause for